Alright, 7.3 continued, still talking about vectors. We were just adding vectors in the previous video. I got interrupted by my first hour class, so I thought I'd continue now. So let's say I've got a vector, I'll call that u right here, and let's say that v looks like that. If I wanted to do u plus v, remember it would look like u and then plus v, and then the resultant vector would be this right there, would be u plus v. If I wanted to do u minus v, well, that's the same as u plus negative v, and negative v looks like this. It's just the same magnitude, opposite direction. So I could do u and then negative v, and then this would be u minus v, or u plus negative v, because v is the opposite direction. So let's say if u was negative 2, 4, and v was, 3, negative 1, and if I wanted to do u minus v, that'd be the same as u plus negative v. So negative v would look like negative 3 comma 1. Just change the signs, then you can add them. So u plus negative v is negative 5, u plus negative v is 5. There's adding component forms. Using these same u and v, what if I wanted to do 4u minus 3v? That would be a scalar vector multiplication. So you can just distribute the 4 to each component, the horizontal and vertical of u. So 4u would be negative 8 comma 16, and then negative 3v, so we're thinking of it as plus negative 3v, so negative 3v would be negative 9 comma 3, and then we can add them. So that'd be 4u minus 3v. You just do scalar vector multiplication. You just distribute the scalar to each component, and that's how it's done. Alright, so what about unit vectors? Anytime we talk about units, usually has to do with 1, like a unit circle has a radius of 1. A unit vector has a magnitude of 1. So if I wanted to find, let's say u was 2, negative 3, and I wanted to find the unit vector in that direction. So u is right 2, down 3. There's my u. So a unit vector would be the same orientation, same direction, just has a magnitude of 1. That's what we're looking for. So what we can do, a couple ways to do it. We could set up similar triangles. Well, we know that u is over 2, down 3, and I can find the hypotenuse if I wanted to. 9 plus 4, so that's the square root of 13. So the magnitude of u is the square root of 13. And then I can draw another triangle. The magnitude has to be 1 because we're trying to find a unit vector in the direction of u. So we know that's 1, so I can call that x, and I can call that y, and I can solve for x and y because these two triangles are similar. So that means the ratio of their sides is the same. So I could say square root of 3, or square root of 13 is to 1 as 2 is to x, And I can say the square root of 13 is to 1 as negative 3 is to y. So I can solve for x, I can cross multiply. So x equals 2 over the square root of 13, and cross multiply here, y square root of 13 equals negative 3, so y is negative 3 over the square root of 13. So my unit vector would be 2 over square root of 13 comma negative 3 over square root of 13. We found the components of this unit vector. Okay, so that's the long way of doing it, where you set up similar triangles and we solve for the given sides. By looking at this, you might be able to see the shortcut. The components of u is 2, negative 3, and the magnitude is the square root of 13. The unit vector is always just going to be u, that vector, divided by the magnitude of u, and that's our unit vector. So u is well, 2 negative 3, but it's u divided by magnitude, so 2 divided by the square root of 13 comma negative 3 divided by the square root of 13. So once you find the magnitude, then you just divide each component by the magnitude and you get the unit vector. Alright, so these are all written in component form. There's another way of writing vectors. It's called linear combination. So if I have 10, negative 3 in component form, it's just another way of writing a vector. U could be 10i minus 3j, and that's called a linear combination. So the i's represent the horizontal component and the j's represent the vertical component. So u would be 10 to the right and down 3, 10 down 3, and this is u right there, written linear combination or component form. Alright, so if I wanted to know the direction of this angle that I just made, I could call that theta. I talked about it in the first video a little bit. We could use some trig. Well, we have two sides. We have opposite and we have adjacent. It is a right triangle, so we can say that the tangent of theta is equal to negative 3 over 10. So then the inverse tangent of negative 3 divided by 10 gives us negative 16.7 degrees. So depending on how it's written, I would probably say not negative. Generally the direction would be from 0 to 360, so we do 343.3 degrees. 343.3 degrees would be the direction of that vector right there. Alright, more stuff about vectors. We can do dot products. So dot products is just an operation done on vectors. If I have u dot v, that's equal to well, the horizontal of u times the horizontal of v plus the vertical of u times the vertical of v, and the result is a scalar. So if I have let's say 4, negative 1, and I have 10, negative 10, 3, then u dot v is equal to 4 times negative 10 plus negative 1 times 3. So negative 40 minus 3, so negative 43. So the result is a scalar, it's just a number, and that is a dot product of u and v. U dot v, that's not times, it's dot, u dot v. So what does it represent? Well, it's in formulas, for one thing. It also can tell you whether the angles are orthogonal or not, or perpendicular. You'll see more of this dot product as the lesson here continues, but that's u dot v. If I wanted to do u dot u, that would be negative, or 4 times 4 plus negative 1 times negative 1. So I get 16 plus 1, we get 17. And if you wanted to find what is the magnitude of u magnitude is the square root of 4 squared plus negative 1, Pythagorean theorem style. So 4 squared 16 plus 1 is 17, so it's the square root of 17. So the u dot u and the magnitude are related in that this is actually, the u dot u is actually the square of the magnitude. So u magnitude. Alright, we're getting there. How do you find the angle between two vectors? So there's a formula for that, and it does involve the dot product. So where theta is the angle between two vectors, the cosine of theta is equal to u dot v over u magnitude v magnitude. So if I have 2 and v is 1 comma 8, we can find the angle between them. So just to show a graphical representation, so 5 2 1 2 3 4 5 up 2, there's u, and 1 8 1 2 3 4 5 6 7. If I wanted to know what is the angle between those two vectors, this is the formula. So the cosine of theta would be u dot v, so it would be 5 plus 16, 21 over u magnitude, square root of 29, 64, 1 square root of 65. So then you just have to figure that out and do the inverse cosine of it. So the inverse cosine of I got 61.07 degrees. So that's our angle between 61.07 degrees, the angle in between those two vectors. I mentioned orthogonal. Orthogonal is just a term used in vectors. It's like the it's one of several words in math that basically means perpendicular. They cross at 90 degrees. Two vectors are orthogonal if they're perpendicular, or if you had u and v are orthogonal if u dot v equals 0. Okay, so if you get 0, that means they're orthogonal. It's also orthogonal if one of the vectors is just the 0, 0 vector. So let's see if I can come up with two vectors that are orthogonal. So let's say 3, 4. So that has a slope of 4 over 3. So I want one that has a slope of negative, that slope is 4 over 3, so perpendicular would be negative 3/4. So rise 3. So if that's 3 and this is 4, that has a slope of negative 3/4. So it would be 4, negative 3. Alright, so let's, sorry. So here's my u, here's my v. U dot v equals 3 times 4, which is 12, and then plus 4 times negative 3, which is negative 12, so we do end up getting 0. These two vectors are orthogonal because u dot v is 0. Now, if u is still 3, 4, and v would be 0, 0, well, we're going to get u dot v to be 0 here, just because the vector is 0, 0. So those are also considered orthogonal. That's the only difference between orthogonal and perpendicular, because if it's orthogonal. Alright, got, maybe I'll stop it right there, and more to come.